Okay, the next problem is problem 9 here. It says, what is the probability that a random drawing yields a green followed by a blue, assuming that the first candy drawn is put back into the packet? So we do have replacement here, which means that when we go to select this, we want a green followed by a blue. So the probability that we get a green is 3 out of the total, which would be 13. And then we put that one back, so there's still a total of 13 left, but now the next one's going to be blue, and there are 2 blues left. So there's our first pick, and there's our second pick. We do have to multiply those probabilities together. That's the multiplication counting principle. So we get 6 over 169, whatever that is a decimal, goes there, 0.0355. And then the next question, are the events dependent? No, because you're putting it back. So when you put it back, you start clean, and they're not dependent on one another. Okay, the next problem says determine the size of the sample space that corresponds to tossing a coin a certain number of times. So a coin has heads or tails. That's 2 possibilities. You know, you could get heads or you could get tails. And if you do that, if you keep writing this tree diagram out for, I'm not going to do the whole thing here, but you will have 8 possibilities because it's 2 times 2 times 2 for the total number of possibilities. So this last row, if you add them up, you'll have 8 heads and tails. So it's 2 to the 3rd power, which is 8. And so 7 times, if you follow the same pattern, will be 2 to the 7th, which is 128. And then that's 2 to the n for n number of times. So that's the multiplication counting principle. And if you draw out a tree diagram, you'll see what that looks like. Okay, the next problem says the probability of an event happening is 1 to 3. So an example of that would be like, say you have 1 green sock and 2 red socks. Then what's the probability you draw a green sock? That'd be 1 to 3. So the odds for E are 1 to 2 because there's 1 green and 2 of the other. And the odds against E would then be 2 to 1. Okay, the next problem says a couple decides to have 4 children. What's the probability they have at least 2 girls? Okay, so what this is the binomial probability theorem, which we're going to raise this to the 4th power. Probability of success plus probability of failure raised to the 4th power. Now, let's call the probability of success having a girl, which is 0.5, so the probability of failure is 0.5. So this one is going to be an easy one because the probability of success is the same as the probability of failure. So let's say the probability of success is 50% of having a girl. So what you do is you then do the binomial expansion here, which would be 4C0 probability of success, which would be P, 0.5, to the 4th power times probability of failure having a boy, 0.5 to the 0th power. Now, this is the probability of having exactly 4 girls. And now if you keep going with this, you'd have 4C1, 0.5 to the 3rd, 0.5 to the 1st. This is the probability of exactly 3 girls. And if you continue this, this would be 4C2, 0.5 squared times 0.5 squared. This is the probability of exactly 2 girls. And you could go on to get the probability of exactly 1 girl with the next term. But what they want is the probability they would have at least 2 girls. At least 2 girls would be these 3 terms added up then. So we're going to have to add those by hand or use the calculator. Okay, so in the calculator what you do is you do this thing called binom CDF. So what you do is you go to second distribution and you scroll all the way down to the bottom because this thing down at the bottom is the binomial cumulative distribution function. And there's explanations on the internet on if you just Google it of how to use it. But for our case we have 4 trials. The probability of success is 0.5 because that's the probability of getting a girl. Now the x value is what gets confusing here because the x value actually means at most. So in this case, we need to do a 1 because if you look at this, we're doing exactly 4 girls, which would be 1 boy. I'm sorry, 0 boys. This would be 1 boy, and this would be 2 boys, and it follows that pattern. So if you kept going down, you'd have 3 boys next, and 1 girl, and the last would be 4 boys, 0 girls. So since we want to add all these up, we want to do at most. So we put a 2 right here, and the reason why is because we want to do at most 2 boys. So that x value, what's confusing about it is it's at most. So I want to do boys because that goes down here, so I want at most 2 boys. Now it turns out we could switch these because the probability of success and failure is the same. So now technically in the calculator, our probability here is standing for the probability of getting a boy, not a girl, but that doesn't really affect anything because they're the same, like I said. So we want at most 2 boys then. That would be adding up all 3 of these terms. And this becomes handy because this would save us time in the bigger problems, but if you hit enter you get 0.6875, which works perfectly. Now the next question wants, what's the probability that all the children are the same gender? That's this term, exactly 4 girls. And then it's also, we got to add the very last term with exactly 4 boys and no girls. Or we could just, since it's the same probability, it's this is 1, and 0.5 to the 4th, this is also 1. So it's just 0.5 to the 4th, and then we want to double that. So 2 times 0.5 to the 4th, which gives us 0.125, or about 12.5%. So the last problem is one more of those then. This time it's not having boys and girls, but it's tossing a coin of heads and tails. So we want the probability of at least 3 heads. So let's call head the success. So we'll call P head, which is, that probability is 0.5. We'll call failure then getting a tail, which that probability is 0.5, so which means they're interchangeable here again. So if you start writing this out, probability of success plus probability of failure for the binomial probability theorem, we're tossing this 6 times, so it would be 6C0 probability of success, which is 0.5 to the 0th power, to the 6th power, probability of failure to the 0th power. So this would be exactly 6 heads and 0 tails. And you could keep going with this. You know, the next term would be 6C1, 0.5 to the 5th power, times 0.5 to the 1st power, and this would be the probability of exactly 5 heads and 1 tail. And you could keep following that pattern, but what we want is at least 3 heads. So if I follow this down, this next term would be 4 heads, 2 tails. Next term after that would be 3 heads, 3 tails. So we want at least 3 heads, so we want to add up all 4 of these terms if I wrote them all out. Or I could add up all 4 of these, and that would be at most 3 tails. So what I'm going to do is at most 3 tails in the calculator. So I'm going to go back to second distribution, and I'm going to scroll down to binom CDF. Number of trials is 6. Probability of success is 0.5. Now, technically, I'm using tails for the probability, which is the same, so it doesn't matter. And at most 3 then is what I want. If I paste that in, that gives me the answer, which is 0.656, or about 65.6%. All right, hope this helps.